Greetings and welcome to the Dr. J Vlog series. It's Monday, April 28th, 2025, and on Mondays, we look into mathematics and statistics. Many people, myself included, have argued over the years that math is everywhere in the world, and it sort of serves as the blueprint of the entire universe in many respects. And so over the years, I've had a lot of fun learning about mathematics, sometimes learning some incredible or mind-blowing facets about math. And one story that I learned decades ago, and maybe you did as well, was the story about folding a single sheet of paper in half and using that folding process as an example of exponential growth or exponential progression. So I thought I'd double check the story before sharing with you folks, some of whom, again, might already be familiar with the idea. So I looked at one popular video on a YouTube channel that has like almost 5 million subscribers. And I wanted to use that as a way of sort of confirming what I was going to be talking about. And sure enough, they had precisely the same example, and they had reached the right conclusion to the following question. And that is, how many times would you need to fold an average size paper, average in terms of thickness? How many times would you have to fold that piece of paper in half over and over again, doubling its thickness each time before you'd reach the moon? So for the record, the moon is roughly 384,000 kilometers from Earth on average. Again, it varies in its distance over the course of the year. And then a sheet of paper is much less than a millimeter thick. So folding the paper in half doesn't really seem like much of an increase, does it? Even if you were to do it 3 or 4 times. So if I take this one normal size sheet of paper and thickness and so forth, and I fold it in half, I'm only going to get a tiny increase, right? You can't even really see that. And then if I were to fold it again, I double the thickness yet again. And there we are, still not much. And then I could fold it again. And in principle, I've yet again doubled the thickness. But do you really see it changing that much? Probably not much. I can do it again, right? And again, look how thick that is. Still not much. And on and on and on. So the question is, well, how many times do we have to fold that sheet of paper, imagining that we could, it'd have to be a much larger, like rectangular size, but imagine we could keep folding it over and over again and in doubling its thickness, okay? Well, the point is of course, even this, after I folded it 5 times, is still only a fraction of an inch, right? It's nowhere near the 384,000 kilometers thick that we need to reach the moon, okay? So what's the answer to the question then? How many folds would it take? Well, again, I learned the answer from this story a long time ago, decades ago. And if you don't know the answer already, you'll be surprised that it's a much smaller number than you probably think. In fact, turns out to be 42. You just need to fold, if you can imagine a sheet of paper rectangularly large enough, you just need to fold that sheet of paper 42 times. And after the 42nd time, you'd actually reach the moon with the thickness, the total thickness of that paper, okay? Now, let me go back to the video that I was examining before I explain what I'm talking about. So again, this is a very popular YouTube channel, and they've looked at the problem, and I thought, well, excellent. Let me see what their numbers are. Let me see how they explain it, and so forth. And so, in fact, they confirmed they reached the same conclusion, the 42 folds, etc. And so I thought I'd use their numbers to create a chart so that I could demonstrate exactly what we're talking about. Well, it turns out they didn't present the numbers in any kind of a chart form. And in fact, I realized that the figure that they actually indicated in the YouTube channel was way off in terms of their starting number. That is the thickness of the paper. So it took me a few moments to figure this out, but they stated that the average thickness of the sheet of paper was 10 millimeters. Now, I didn't really give that much thought. And they even put up a graphic, 10 millimeters and so on. Turns out that's wrong. The average thickness of a sheet of paper isn't 10 millimeters. It's actually 0.1 millimeters, or 0.10, same thing, 0.1 millimeters. So I don't know how somebody made a mistake. In effect, they're off by a factor of 100. And so when I was putting it into an Excel file and I was creating this chart, I thought, this isn't right. I'm reaching the moon much sooner. Okay, and more importantly, by the logic, what it means is that because they were off by a factor of 100, you end up arriving at the moon 2 steps sooner, after only 40 folds, 40 doublings, instead of 42. So again, I had to figure out what the heck was going on. And so for the current video, we're going to actually start with the number that's quite proper and that's correct. That is, we're going to start with the 0.1 millimeter thick sheet of paper, like the one that I was using. Not 10 millimeters, 0.1 millimeter. All right. And here's the explanation then for how we arrive at, or how we can reach the moon then in only 42 doublings of this single sheet of paper of normal thickness. Okay, so obviously if we start with 0.1 millimeters, that's a tiny fraction, right? We double that, we get 0.2. We double it again, we get 0.4 millimeters. We double it again, 0.8 millimeters, then 1.6 millimeters, and then 3.2 millimeters after 5 doublings. That's still a tiny, that's not a lot. But it's not the amount, it's the rate of change that matters. We're doubling the size each time. Right? So if you imagine starting with a person, say, who's 6 feet tall, and you double that person, they'd be 12, and after you double them again, they'd be 24 feet tall. Well, of course, that would be unimaginable in human terms, and that's only with 2 doublings. So it's that rate of change that matters, all right? And so, again, this is what it kind of looks like in graphic form, right? And again, after 1 doubling in time has passed, the initial population of any exponentially growing population or size always increases by a factor of 2. So that 2 times there. And then the same unit of time, or the same increase, leads to a 4-fold increase. Okay? And each doubling, we double the total size by a factor of twice what it was previously. So we go from 2 times the size to 4 times the size to 8 times the size to 16 times the size, and so on. Okay? And what you should really notice there is, notice how you see the slope of this curved line here? Notice how that changes. It starts getting steeper after each doubling. All right? And that's only going to continue slope-wise. It's only going to continue to increase, and even more dramatically. All right? So that's what's important. That's the core principle behind what we mean when we talk about exponential growth, the logic of which can be applied to any type of growth. If you're talking about investment growth, you want your investments to grow ideally exponentially to the size of populations, to the doubling of a sheet of paper. Okay? And so at the 6th doubling, by the way, to go back to the paper example, you're now up to 6.4 millimeters, then 12.8, then 25.6, and the overall number starts to grow larger much more quickly. After 16 doublings of this single sheet of paper, we've arrived at almost 66 meters in thickness now. 16 times. We've doubled this sheet of paper, in principle, 16 times, folded it 16 times. And by the 16th time, we're now, I can't obviously show it, we're now at 66 meters almost in thickness. All right? So, and by the way, we say that after the 16th doubling, what we're talking about then is a factorial, or an increase by a factor of 2 to the power of 16. Right? So 16 becomes the exponent, 2 to the 16th power. And again, that's literally what we mean by exponential growth. Right? And then by the 20th doubling, again, you're not going to be able to see it very well here on this particular screen, but by the 20th doubling, taking this initial example of the 0.1 millimeter sheet of paper, we've now passed 1 kilometer in total thickness. And by the 30th doubling, we've now passed 1,000 kilometers. And then finally, by the 40th doubling, we're in David Bowie's space territory. Now we've passed 100,000 miles, not miles, it's actually kilometers in this example. But literally, we would have passed 100,000 kilometers. And then the next doubling, the 41st doubling, puts us at almost 220,000 kilometers thick. So now, if the moon's 384,000 kilometers away, we're more than halfway there. Okay? So only one more doubling then, the 42nd doubling, takes us to almost 440,000 kilometers and in thickness. And recall, with again, the moon only being 384,000 kilometers away, we're now well beyond that figure. So we've gone well past the moon on the 42nd doubling. Okay? So exponential growth then is an incredibly crucial concept in nature, in tracking populations, in looking at one's finances, as I mentioned a moment ago, in tracking rainfall and sunlight or the spread of disease, a whole range of different issues. So basically anything where you can track the growth and the size of something or of some kind of a phenomenon. Okay? Imagine, for example, an invasive species in a lake. You could track what happens or how quickly that invasive species multiplies within the lake. All right? One good example of that is the zebra mussel, which has afflicted some of the lakes up here in Ontario and other places. Because of the zebra mussel's incredibly rapid and almost exponential growth rates, once they're introduced into a new environment, if left unchecked, they'll quickly take over the entire and often disrupt or destroy an ecosystem. Why? Again, because their growth rates are almost exponential in nature. So that can be devastating if left unchecked. So yes, there are these fascinating mathematical properties associated with exponential growth, but we can also study growth in nature and looking at all kinds of practical applications as well that become relevant when we start to study growth patterns, such as how rapidly or an aggressive type of cancer, for example, might spread throughout one's body. And on the right side, we can also imagine positive forms of exponential growth, such as can happen in the case of the buildup of antibodies, right? Or the growth of YouTube subscribers. Hey, now that's a good idea. If each of you watching this particular video or any of my videos were then to go and recruit 2 new viewers, and then if you got each of those new viewers to recruit 2 more, and so on, if that was the message, what would we have? What would we have? We'd have a classic example of exponential growth. So do me a favor, hit the like, subscribe, and alert buttons, and go and recruit 2 more people. And make sure when you recruit those 2, tell them to also recruit 2 more people. And if we keep that process going, pretty soon we'll see the exponential growth of the Dr. J vlog series. Instead, what do we see? We see, in the case of my own work, my own YouTube channel, what we call an arithmetic growth. That is based on a simple principle of adding a fixed number of units over each period of time. And that's literally, in my case, been about 1 viewer per day on average since I started posting daily back in the beginning of January of this year. So what does that mean? Well, if there's no change in the pattern, that means I'll actually get to about 1,000 subscribers sometime around the start of 2028 or close to there, right? Well, I don't think Mr. Beast, aka Jimmy Donaldson, with his 387 million subscribers, really needs to worry about me taking over the crown for the most subscribers anytime soon. But I am thinking about doing a counting video, maybe counting to 1 million or something like that. And that would allow me to, illustrate, I think, quite nicely the nature of arithmetic growth. And maybe by demonstrating arithmetic growth, that might lead to exponential growth of my YouTube channel, right? So do I need to resort to these kinds of stunts to increase my viewership? Or would it just simply be an excellent pedagogical demonstration, a good example of arithmetic progression if I would just sit here and talk in front of the camera, 1, 2, 3, 4, etc., until I reach 1,000,000. It takes a while to do that, by the way. You can figure out how long. Depends on how quickly you can speak, what the unit of, increase is per second. Anyway, let me know in the comments if I should do a counting video or demonstrate arithmetic progression in that fashion or in some other entertaining fashion. But in the meantime, as ever, may you and yours continue to create peace in your lives, nourish love in your hearts, and dole out hugs arithmetically. Well, heck, dole out hugs exponentially. We'll see you soon.